Okay, how's everybody doing? Can everybody hear me okay? Oh, great. Let me turn this off. All right. Okay, so I think we still have a few more joining, but go ahead and get started. And so, okay, JT's here. All right, so thanks everyone for doing the WebEx. It's kind of like Zoom. So it should be kind of like a normal class, but I'll try to walk you through today's material, just doing this. And if something happens and you lose connection or something like that, I am recording the meeting, and you can access this material whenever you want, in case anyone can't be here or has to leave early or something like that. But I appreciate you again being flexible and doing a remote meeting. But I think most of the rest of our meetings will be in the classroom, and I couldn't make it today, but I'll try to make this as a normal class as possible. So let's just check where we are here. Okay, so I've done a WebEx or a Zoom before. I'm sure you have, but just in case, you're welcome to turn off your microphone or turn on your microphone with any questions. And then there's also a chat feature that looks like Lauren already posted to, but let me post here. Okay, so you are welcome to post anything to the chat, and I'll try to check that chat feature throughout the meeting. Or you can unmute your microphone and ask any questions or ask me to repeat something if you want to do it that way. Okay, so we are on week 4. And I think we're fairly caught up. The assignments 1 and 2 and 3, we've gone through all that material, and so those assignments should be done. I think they're all due today, and so try to get those in if you haven't done that. And then we'll start week 4. We'll start assignment 4. Assuming we get through all of the material, that'll be due next Wednesday. Okay. So what I want to do today is go back to the business stats textbook. A little hard to do linear algebra and matrices via Zoom, so we'll come back to that next week. But I do want to cover, jump ahead a little bit in the stats textbook because we've got a lot of chapters, and I don't want to get too behind, but I want to cover kind of the important things in the class. And so we're going to do hypothesis testing today, and I believe that's chapter 9 is what I want to cover in this lecture. So I posted some stuff for this week's material. Okay, so here's week 4.
Can you hear me?
Yes, I can. Can you hear me?
Yeah, sorry I'm a little late. I had some Wi-Fi problems and I was installing WebEx on my phone.
All right, no problem. Thanks for joining. Glad you can make it. And yeah, just you can go ahead and turn on your microphone whenever you have a question, or you can use the chat feature. So this is week 4, and what I want to cover in this week is chapter 9 in Anderson. We'll skip ahead a few chapters, and if we have extra time, we can cover some chapters we skip. But there's a couple chapters on more advanced probabilities and some other intervals and stuff like that. But I do want to get to this so we can cover hypothesis testing, which is important, and then get into different types of regression and how to use this type of analysis. And so this is going to cover chapter 9 in Anderson, or the business stats textbook. And then we'll start going through some of the material and assignments. And then once you got a good feel for that, if we get through everything, this will also be due next Wednesday. Okay. So I want to start by introducing hypothesis testing. And let's start by, well, let me pull up chapter 9 in Anderson. Okay, here we go. Okay, so what we're going to introduce in this chapter is how to set up hypothesis tests and to set up the appropriate test for the appropriate research question. And then we'll use that in more advanced models. But usually, when we have uh, some kind of research question, we want to test the fact that our research hypothesis is in fact valid, and if there's anything in the data that it's that the relationship in the data holds strong enough that you can kind of reject the fact that there's nothing and at least confirm that you found something. And so that's kind of what we'll set up is if you think there's something in the data, or you think there's something in some research question, then you want to set up the fact that I think at least this is bigger than this, or this is less than this, or there's something in the data that it is not just nothing. And when you kind of set up the test, then that will confirm that you can kind of go ahead with your research project. So let me show you what. Start here with a couple examples, and that'll give us an idea of how to set these up. Right. So the very first thing is just to kind of to learn how to write the hypothesis, and you're going to set up a null hypothesis, which you're trying, or the goal is to reject it. And then usually the alternative hypothesis is what you're trying to prove, or what you're trying to at least say that the data is strong enough that there is something in the data that I can talk about and use my data to prove. So if we look at exercise 2 on page 402, all right. So first one, actually first exercise for your homework is exercise 2 on page 402. So this should give us an idea of how to set up these hypothesis tests. So bonus plans effect on automobile sales. So the manager of an automobile dealership is considering a new bonus plan designed to increase sales volume. So currently the mean sales volume is 14 automobiles per month, and the manager wants to conduct a research study to see whether the new business plan increases sales volume. Collect data on the plan. A sample of personnel will be allowed to sell under the new business plan for a 1 month period. So if mean sales volume is 14 automobiles per month, and the goal of this plan is to increase it, then we're trying to reject the fact that uh, mean sales are 14 or they're bigger. So let me set that up here. Okay. So let's start this. Okay, so usually we'll have some simple notation where it's like H0 or like H naught, like this. Okay. Let me make this like a little subscript. Okay, so the null hypothesis is what we're trying to reject, and usually the alternative is what we're trying to prove. So let me just. Okay, so it's usually something like that. So that H0 or H naught is a null, and then the alternative is the opposite, or not the opposite, but the alternative, or what would be the case if this was not the case. So, okay, so for this question, the null hypothesis would be that this plan does not increase sales, and the null would be that sales volume is 14 automobiles per month or less, because if our plan doesn't increase that, then the null is true and there's 14 or less. So basically, the null would be something like it's less than or equal to 14. Right? And then the alternative would be that the program actually works, and the sales are greater than at least bigger than 14, because that means we're increasing it above the average. Okay. So develop the null and alternative hypothesis for most appropriate for this situation. So like we showed here, If like use that's the mean. So if the mean sales volume is less than or equal to the average or the mean, then this program isn't working. If we can reject that, then that's our research, what we're trying to prove. Then we can prove that if it's 14 above 14, 15, 16, whatever, then at least using this program you're getting more sales. So if it's leading to more sales, then you can conclude that the null is not true and that the alternative is true. So part B would be part A to set up the tests. All right, then B is comment on the conclusion when H naught cannot be rejected. Okay, oops, sorry. So if H naught can't be rejected, that means that this program doesn't do anything or it's ineffective in increasing sales, and that we're not getting any more sales than we did beforehand with the new program. Right? And then comment on the conclusion when H naught can be rejected. That's our research hypothesis. All right, so when the null can be rejected, then we conclude that the program is effective and leads, or at least coincides with, an increase in auto sales. So it could be that we started the new program and there's like tax return time or something else is leading to new sales. So we couldn't say definitively that uh, this program specifically is increasing the sales, but we can say that when the program started, there was also new sales. So we at least know that something happened when the program started. Okay. Okay, so no, no, nothing into the chat yet, but let me know if you need me to go over any of this stuff again. But that's the general idea of how you set up these tests, and we'll do a bunch of these. But the idea is that you want to set up the thing that you're trying to prove or disprove, and the alternative is what you're trying to prove, and then you got to know what you can conclude if this is rejected or not. Okay. All right. So the next one on the same page is exercise 3, filling detergent cartons. And this will give us an example of doing a similar type of analysis, but also working with a different, like sometimes you got to flip around the inequality or change it to an equal sign even based on the research problem. So this is number three, and this will be a similar analysis, but a little bit different of a problem. Okay, so this was number two. All right, so it's not auto sales, but I just copy and pasting it so I don't have to do the subscript thing and with the null and the alternative. But let's define our problem here. All right, so a production line operation is designed to fill cartons with laundry detergent to a mean weight of 32 ounces. All right, so 32 is our target, and a sample of cartons is selected periodically and weighed to determine whether whether underfilling or overfilling is occurring. If the sample data leads to a conclusion of underfilling or overfilling, the production line will be shut down and adjusted to obtain proper filling. All right, so let's formulate the null and alternative that will help in deciding whether to shut down and adjust the production line. So if we're hoping that our detergent is right around 32 ounces, that's 32 ounces. That's what we're trying to prove. So essentially, the alternative would be that anything other than 32 is what we're trying to reject. So um, basically, the alternative is it's not 32 because we're trying to prove that it's if that's what we put on the carton, that's what we want it to be. I mean, it's probably not exact, but we want the detergent to be 32 or 32.1 or 31.99 or something close. And so we at least have to determine if the cartons are being filled to their proper ounces weight. So there we go. Okay, so in this case, it's a little bit different because it's not bigger than or less than or less than or bigger than. It's the fact that we want to prove that our detergent is 32 ounces. Okay, so that's a not equal to sign there. So the alternative is the detergent ounces are not 32. Right, and then the alternative is it is 32, like we're trying to prove. Uh, that's the research question. Then so we go about answering the other questions based on the fact that is it not this or is it this? Okay, so comment on the conclusion and the decision when H naught cannot be rejected. Okay, so when the null hypothesis cannot be rejected, that means that there's enough evidence to say that these detergent bottles are not being filled to their proper weight. They're either underfilled or overfilled. Either way, that's a problem because if they were, well, I'll write it here. So now, either when the null hypothesis cannot be rejected, we can conclude that the detergent bottles are not being filled to 32 ounces, which is the weight listed on the bottle, and that's a problem for two reasons. So if we underfill, that means the customers are getting gypped; they're not getting what they pay for. If the bottles are underfilled, customers are not getting their money's worth, and then if the bottles are overfilled, that's also a problem because then the company's wasting money on extra detergent that it didn't say it put in the bottle, so they're overfilling with extra inventory. If the bottles are overfilled, the company is spending extra money on detergent inventory that it doesn't need to spend because it only needs to spend the amount of 32 ounces, right? So it's a little bit different interpretation, but if you set up the null and alternative properly, then you can still kind of interpret the results. And then part C is what happens if we can reject the null. Right, comment on the conclusion and the decision when H naught can be rejected. Okay, that would mean that the detergent bottles are on average filled right to their proper weight, and no further investigation needs to be done. And it looks like the company is doing a proper job in filling these bottles. Right? When the null hypothesis can be rejected, that's what we're looking for. The detergent bottles. The detergent bottles are filled to approximately 32 ounces, like the label says, and then no further investigation is needed because that's what the bottles claim that the ounces are. Okay, so that's the general idea. They'll get a little more complicated, but what you want to do is set up the null based on the research questions, set up the alternative, and so once you state those, then you can determine what happens if I reject this, what happens if I don't, and then what's the research problem going forward. Okay, so if there's any questions with how we set these up, just please let me know. You can again post anything to the chat, or you can turn on your microphone, ask any questions, or I'm also happy to repeat anything that was missed. Okay, so it seems like getting the idea so far, but let's keep going with this concept. So the next one, and I got a bunch of terminology. This document has some additional pages that I want to go over. I took some key things out of the chapter. When we get to that, we'll go over that too. But let's um, look at exercise 6 on page 405. And let me see if we've got there yet in terms of material. All right, so this one, again, it's good to get practice. Oh, actually, I want to introduce. So we got the idea of how to set up the hypothesis, the alternative, the null, then the alternative, and then what that means if you reject the null or if you don't. So basically, there's two specific types of errors that you can across when you're doing this kind of analysis. And it explains that in the chapter, and I also put some stuff in the chapter 4 document here. Okay, so if everybody can see this, this is table 9.1, which is an important table from chapter 9. And this lists the two possible types of errors and correct conclusions in hypothesis testing. So there's two things that can happen. Either you accept the null or you reject it, right? So if you accept it and the null is in fact true, then that's the correct result. But there is a chance in doing these type of analysis that you accept the null, and in fact the alternative is true, and that's what we call a type 2 error. So a type 2 error, and they'll come up a lot in this chapter and going forward, is that if you accept the null, it's true, and in fact it is not true, then that's what we call in stats a type 2 error. So a type 2 error is accepting the null when in fact in reality it's true. But if you reject, so that's the case when you accept the null. If you reject the null, um, there's a chance that it is in fact true, and that was a type 1 error, or that is a type 1 error. And if you reject it, that's correct, then there is no error. So either there's two things that can go wrong doing this type of analysis. It's accepting the null when it is in fact true. I mean, when it is in fact false, and that's a type 2 error, or rejecting the null when it's in fact true, and that's a type 1 error. Okay, so when you hear these type 2s and type 1s, that refers to different situations when you either accept the null when it's not true, or you reject the null when it is true. Okay, so you can refer to these concepts for the next question. So basically, we're going to set up the alternative and the null, and then comment on type 1 and type 2 errors in this context. So exercise 6 on page 405 is going to we're going to set up what we did before, talk about it, and then comment on the two types of errors that can result for these hypothesis tests. Right. So page 405. Questions, exercise 6. All right, so this one is concerning orange juice labels. So the label on the 3-quart container of orange juice states that the orange juice contained on average 1 gram of fat or less. All right, so let's answer the following question and set up the tests if this is the claim. So if the claim is that the orange juice contains 1 gram of fat or less, uh, that is what we're trying to prove. And if there's more fat than 1 gram or than 1 gram, then that means that the null is true. Okay. Sorry. So part A is develop the appropriate null and alternative hypotheses. Okay. So if and sometimes it's like sometimes you can go backwards and set up the alternative first if you want. So we're trying to prove that orange juice contains an average of 1 gram of fat or less. All right, so if the orange juice contains less than or equal to 1 gram of fat, that's what we say on the label, and that would in fact be what is what we're trying to prove in this research question. But what if if we do some tests and it turns out there's more fat gram, then that would mean that the alternative is true or the null is true, and we'd have to do some research or at least rechange our labels because they're not accurate. So if the orange juice contains an average of more than 1 gram of fat, that's the null. All right. So we're trying to confirm that the orange juice has what it says in the label, but the null is that it doesn't contain that, and there is in fact more than 1 gram of fat per whatever it is per average. Right. So what is the type 1 error in the situation? What are the consequences of making this error? So recall that a type 1 error is rejecting the null when it is in fact true. Okay? So if in this case, if we reject the null, it's in fact true, that means that we said the orange juice doesn't have more than 1 gram of fat, but it actually does. Right? So type 1 error is rejecting the null when it is in fact true. And then the consequences are claiming that the juice has less than 1 gram of fat. But in reality, the juice has more than 1 gram of fat. And then that's, yeah, so that's the type 1 error in this context. Okay, so what is the type 2 error in this situation? What are the consequences of making this error? So this is the opposite. Okay, the more common error, the type 2, is accepting the null um, when it is not true. Okay, so type 2 error is accepting the null hypothesis when it is, in fact, not true. Okay, so then we're saying that there's more than 1 gram of fat, uh, which is what we didn't want to prove. But so it's even worse because we said it's wrong, and then in fact it was true. So right, so the consequences are finding the juice had more than 1 gram of fat, but it actually, but in actuality, the juice had less than 1 gram of fat as stated in the label. So this type 2 error is finding what we didn't want to find, and then in fact that was wrong. So those are the different types of errors. And if there is an error, it's got to be either a type 1 or type 2. Okay, so why don't we look at the next one and apply the first set up the hypothesis test and then state the errors and what they mean in this context. All right, so exercise 7 on the same page is on carpet salesperson salaries. And so we're going to set up the null and alternative and then talk about the chances and what they mean for the different types of errors. So exercise 7. All right, so here's carpet salesperson salaries. Carpet land salespersons average $8,000 per week in sales. Steve Toyce, the firm's vice president, proposes a compensation plan with new selling incentives, and Steve hopes that the result of a trial selling period will enable him to conclude that the compensation plan increased the average sales per salesperson. So I think this one it's easier to set up the null first. So if they uh, increase, okay. So if the average is $8,000 per week, that's the null. Or actually, because we're trying to increase salesperson salaries, then the null would be less than $8,000 per week. Okay, the null is carpet salesperson salaries are less than or equal to $8,000 per week, which is what was the case before anything happened. Okay, and then the alternative would be that the compensation plan is effective and it increases the salesperson's average salaries by at least more than $8,000 per week. Right, so uh, that's the setup there. Right, so if the plan is effective, then their salaries will be at least bigger than the default or the status quo, and they make more than $8,000 per week. All right, and then what is the type 1 error in this situation, and what are the consequences of making this error, given this different research question? So the type of error is defined the same, but the implications are a little bit different. Right? So a type 1 error is, like it says up here, and like we learned, is rejecting the null is in fact true, right? Okay, so if you reject the null, um, and your conclusion is wrong, and that is in fact correct, I mean, if you reject it and it's true, then that's a type 1 error. So type 1 error in this problem is rejecting the null when it's true. So if you reject carpet salesperson salaries are less than $8,000 per week and conclude that they're bigger than that, and in fact they're that or less, then that's the problem, right? That would tell you that the plan works when in fact it doesn't work. So a type 1 error in this problem is uh, rejecting the null when it's in fact true. And if you reject, sorry, if you reject the null when it's in fact true, that means you're claiming that salesperson salaries have increased to greater than $8,000 per week, the compensation plan, but the error is in reality the plan has not worked. Salaries are unaffected, meaning that they still earn $8,000 per week or less. Right? And then the type 2 error is the opposite. So a type 2 error, the more common type, is accepting the null when it's in fact true. And accepting the null when it is not true. So in this problem, that would be saying that salesperson at the carpet store, Carpet City, or whatever it is, don't make any more money with the plan. So that's not what you not that's what you don't want to prove, but in fact they do. So you said something you weren't looking for, and in reality the opposite was true. there's the type 2 error in this defined in this context. Type 2 error is concluding that the plan doesn't work. There was a type 2 error, and the actual conclusion should have been that the plan does work. And in reality, carpet salespeople actually make more than $8,000 per week with the plan. So the error is saying that the plan doesn't work. In fact, it does work because you made a type 2 error in this context. All right. Okay. So hopefully we get the idea of number one, setting up the null and the alternative, and then defining those in different contexts depending on your research problem. What it means to accept, reject those, and then what the two types of errors could be and how they can be interpreted, and what the consequences are for different types of research problems. Okay, so we'll do this. We'll try to set up some of these tests in Excel in a little bit. I do want to introduce a few more things before we do that. All right, so we define the two types of errors that can occur, type 1 and type 2, right? Okay, and then once we start looking at real data and like significance levels and what's the probability of making an error for different types, uh, the level of significance. Yeah. Um, so yeah, can you show me the last um, for the so just 1 second. I wanted to re-show the last answer for one of the students. So 1 second here. Okay, great. Okay, so no problem. If you need me to repeat anything, just let me know and I can go back to that. But we were going to move on past the errors. All right, so here's the type 2 or type 1 error, and then a level of significance when you're looking at doing data analysis is the chance of essentially making a type 1 error. So usually when you're doing a research problem, your goal is to accept, sorry, goal is to reject the null, and then that would conclude that your research question is in fact correct. Now, if you reject it, that was a mistake, then that's a type 1 error. So the level of significance is the probability of making a type 1 error, rejecting the null, but when in fact the null is true, right? So you're gonna have some type of probability of making a mistake in your research, and the mistake or the level of significance is the chance that you made a type 1 error. So if you reject the null and okay, so let's say that your level of significance is 5%, would mean that the chance that you made a type 1 error is 5%. And if it's 1%, it's 1%. So the level of significance is the chance or the probability of making a type 1 error, rejecting the null, and the chance that in fact that is true. So that's what, when we're looking at different levels of significance, that's what we're referring to in this concept, is making a mistake on rejecting the null, and there was a chance that it was in fact true. Okay, so we've kind of talked about, we've kind of done these indirectly, but a one-tailed test is setting up the null where the null is than or equal to something, and the alternative is being less than, kind of like the fat content in the orange juice. And or it could be this type where it's less than or equal to something for the null, and then the alternative is greater than. Right. So if you're setting up a one-tailed test, it's the fact that the alternative is one direction and the null is a different. Let me scroll down to what I mean by that, because there's a one-tailed test and there's a two-tailed test. So this is one-tailed, right, and this is two-tailed. And I'll go back in a second, but just to kind of explain the difference. So if you're doing the fact that H naught is an equality, or vice versa, that's a one-tail. Sorry, a two-tail. And if you're doing a greater than or equal to thing, then that's a one-tail. So we've done both of these in practice already, but if you're looking at the idea is if you're looking at equalities and inequalities, that's a two-tailed test because you're looking at disproving above and below. But if you're just looking at greater than or equal to or less than or equal to, you're only trying to prove one direction, so that's a one-tailed test. Okay, now we'll encounter something later on, or pretty much when we start doing analysis in Excel or RStudio or something, some kind of statistical package, you're going to get test statistics or T statistics, and those are calculated like this. So it's important to understand how they're calculated. But when we start doing this in practice, you don't really have to do the calculation because Excel or the software program is going to do it for you. But I do want you to understand how it's calculated. So this is the simple way in which it would be calculated. So here's the mean. All right, so if you're looking at the t-stat for some uh, hypothesis test, right, this is the mean. You subtract the cutoff value, so like this would be, okay, so that U would be, in this context, 8,000, because that's your research question, and then in this context, 1, it's whatever the number you're trying to go above or below is. Okay, so this is the standard deviation, and then this is the number of uh, observations. Okay, this is the way that the stat is calculated. It depends on all these things. We'll do a couple calculations in Excel, but I just want you to understand how the equation is calculated. But going forward, when we start doing analysis, you'll kind of get this calculation automatically, and kind of as a result of your estimations or output. And the importance is knowing, well, number one, how to calculate it, but number two, how to use those critical values and how to make inferences based on those critical values. So basically, to confirm the significance of your result, you can look at the test stat or the t-stat, which I just defined here, this equation 9.1. or you could look at the p-value, and either one in theory should give you the same result. What you're looking at, if you've done some statistical analysis, is to find a big enough t-stat or a lower enough p-value, and either of those would confirm the result, where a p-value is the probability that provides a measure of the evidence against the null provided by the sample. So smaller p-values indicate more evidence, and conversely, higher t-stats indicate more evidence. So if you get a good result, you should have a high t-stat and a low p-value. Okay, and if you're looking at based on the level of significance, usually it's something like 0.01 or 0.05. If your p-value from some result is less than that projection rule, you can go ahead and confirm that your result is true. But if your p-value is too high, then you can't confirm the result. Right, and then similarly, for the t-test version, you would reject the null if the critical value is bigger than is at least bigger than the critical t value, or critical, in this case it's a z, but you're calling it a t value in the regression results. So the idea is that you can reject the null or confirm your results in two ways. Either you get a high enough t-stat, or you get a low enough p-value. Okay, so those are explained a bit more, and we'll do some Excel calculations of those. But we start interpreting like regression results or results from some analysis. You have the choice, or you can do both, is to look at kind of the critical t-scores, see if they're bigger than a critical value, or you can look at the p-values and see if they're low enough. So in kind of the rule of thumb, you want a big enough t-stat or a lower enough p-value, right? So you're trying to get a big enough t and a low enough p-value. So in a two-tailed test, you're looking at inequalities versus equalities in a null versus alternative. So like it says here, for a two-tailed test, the p-value is the probability of obtaining a value for the test stat as unlikely or more unlikely than the value provided by the sample. So if you're trying to say that, if you're trying to prove that the the result is some critical number, then the alternative, or sometimes the null, would be that it's not that. So this is a two-tailed where you're looking at it's this or it's not this. Remember that the one-tailed was looking, is it bigger than this or less than this? Okay, so this kind of shows you what, assuming there's a normal distribution like you see here, then this is a good picture of what's going on. So this whole region, right? If you go one way or the other, like let's say you reject the null, and you have some chance of it being wrong. And this whole area, it's like the light blue, is you're good to go. There is a chance that you're in these little tails over here. If you're in that area, then there's a chance that you made a mistake. So if you view the research question kind of like this, and let's say that you reject the null hypothesis and confirm your result, then you can look at it look at it as like this is the chance you're correct, but there is a chance like these little um, lower darker blue areas that you're wrong. So uh, the probability that your actual result is incorrect can be represented by these little ranges down here. So this is like think of it like this is like 95% of the chance. There's a 5% chance that you're wrong by going too low, too high. Okay, now same thing for uh, what was this? Okay, this is the p-value approach, and this would be the uh, critical value approach, but it's the same thing. So the idea is that, like I said before, you can look at the p-value approach or the t-statistic approach, and either way, you're representing some fact that I'm pretty sure of my result, but there's a chance that I'm wrong. So the chance that you're correct can be represented by this kind of blue area in the normal distribution, but you can represent the fact that these are the critical values like 1.9 and 1.9, and there is a chance that um, I was wrong, and that could be like if you're up here in this kind of unlikely area, or this other one down here, you can see there's like a lower region and a high region. So kind of like 5% chance that your result was incorrect, and be represented by these little pictures where uh, this is this is saying that your result is true. This is saying that you made a mistake. Um, but normally, like your mistake is like there's a 5% chance or a 10% chance I made a mistake. Okay, and let me revisit this. Yeah, so this directly relates to the level of significance. So the level of significance is the probability of making a type 1 error. And the null is in fact true. So let's take that and look at the pictures again. Right, so if you reject the null and you're looking at a 5% significance level, then there's only a 5% chance that you're in this little region or this little region. So those little extreme low values or high values represent the fact that your conclusion could be wrong 5% of the time. And the same for this one. So if you're looking at a 5% significance level, this would show you that there's essentially a 2.5% chance up here above this 1.96, and a 2.5% chance that you're below this negative 1.96. But 95% sure that you got the correct result. Okay, and let me make this a little bit bigger, but this is important because it shows you that um, you can see how uh, what this shows you that if you have enough samples, um, you can get away with like a lower p value or a higher p value. It's just going to increase. So look at this. All right, so if you have a sample size of 10, which is really small, then your t value is probably going to be small, and your p value is probably going to be high, and you probably can't get at any conclusion. But if you get up to 100, you can see that just by getting lots of observations, let's say you get let's say you had 1,000,000 observations, then there's almost a guaranteed chance that you're going to accept the conclusion because you have enough observations to prove it. So the more observations you have, the more sound your results are going to be, and the less you have to be worried about the t value or the p value. But if you have a small number of observations, then you got to be really important on how you interpret your results. So it's not always possible, but the best um, method for any research question or any conclusion is get as many observations or samples as you can, and that will help very much in determining if your result is true. So I mean, obviously, it's pretty hard to get a billion samples or a billion observations, but more data the better in confirming that your results are true. Okay, then what's next? Okay, same, yeah, same for this. So this was another result showing that um, more samples you have, and the less you got to be worried about the z value, or the t value, and the p value. So pay attention to your critical tests, which are the p value test and the t stat test. But also, if you can get lots of observations, that's the best way you can kind of like communicate to the audience or the researcher that your results are sound. Is once you get um, enough observations, you're pretty sure that your whatever you found is going to be true. Okay. Now I want to look at a couple examples of trying to do this process in Excel. And there's an example on page 414 and 424 that we can pull up a worksheet and kind of uh, do some of these analyses. Okay, so again, let me know if we covered some kind of new material. Some of it might be review and some of it might not be, but um, if you need me to show anything again or kind of repeat any of these concepts or examples, then please um, post whatever to the chat, or you can unmute your microphone to ask questions. But if we don't have any questions, then let's look at figure 9.7 on page 414. Let's see if I can make that. Okay, so what we're going to try to do here is to replicate this little analysis of calculating the sample size, sample mean, and then the p-values and t-stats. All right, and then you can use the same formulas or template to do it for other tests or other research questions. So if you can open up now or whenever you're doing it, the golf test Excel file. It's under chapter 9. Okay, so it really got it. It's already got it there for you, but let me just kind of walk you through what's happening here. Is so if you pull up the golf test, this is different yards. Like this is how far the drive is. So different observations. There's a number of them here, and it's only showing you a part of them. But in this case, there's 500 observations, right? And what you want to do is kind of set it up like this. You're going to calculate a sample mean, or sorry, a sample size, which is the number of observations. Okay, just basically count the number of observations. A sample mean, which is the average. You can get the standard deviation, which is given to you, is 12, and you're trying the hypothesis here is to determine if. Actually, let me read you what we're trying to prove here. So this is like a golf flight text, golf flight test looking at if the golf balls go a certain amount. So what you're looking to prove is do they go? The claim is that do the golf clubs do what they say and go 295? Um, and if they don't go 295, there's two reasons why that can occur. So if they're less than 295, that means that the balls are not going far enough, and if they're more than 295, that means that the company might be charging an incorrect price because you're claiming something and they're getting more for their money. So either way, the company is either selling the customer short or not using the proper model and overstating or I guess understating what the product can do. Which page? 414. Okay, so null here is that the average is exactly 295, and the alternative would be that it's not. Right? So this is the standard error calculation. This is the calculation of the t-stat from that formula from your textbook, and this would be the p-values, depending if you're looking at a lower tail, upper tail, or two tail. Okay. So what I guess we can do is just kind of get an idea of how you would calculate these. I'm going to put this stuff over here, and then show you how to or just kind of walk you through it in the data page. Okay, so if you want to just, I guess, cut and paste this whole area and move it to the data page, you can see how these numbers were determined. And then the ones that have no reference, that's because we have to specify the sample in this context, right? So I just wanted the labels to work with. Okay, so to get the sample size, you're just going to count the number of observations, which is count A2 to A51. So you should get that there's, I mean, you can just see that, but you can count the number of observations in this column, which is 50. There's the yards, and there's 50 observations. All right, so if you use the count function to count the whole range, that's just 50. The sample mean is the average of all these yards observations. So the average of A2 to A51. All right, so the average is about 297. So the average is a little bit above we think it should be. It's just 295 is the target. So the standard error, if you recall that from like chapter 3 or chapter 4, sorry, that is the standard deviation divided by the square root of the sample mean, or the square root of n. So this the standard deviation is given is 12. If you divide that by the square root of the number of observations, which is 50, it's our standard error. And then the test stat, or the t-stat, is calculated based on the standard error. So the test stat is the mean minus the hypothesized value divided by the sample mean. So here we're using this equation. Right there. All right, so this is this equation 9.1. That's what we're calculating right here in this little worksheet. All right, and then this is calculating a lower p-value, a upper p-value, and then a two-tailed test. So if we're looking at it's going like greater than or equal to, or if we're doing a two-tailed test, which is just does it equal this, or does it not equal this? So this little normal distribution, if this t-stat is true, and this is like this number would be like the cutoff point in that picture here. Right there, that the probability that that number is less than that would be your p-value. Okay, so it should calculate it for you, but if you look at the normal standard distribution of the t-stat, it's that. And if you look at the upper tail, which is 1 minus that, and the two tail, if you're looking at is the value 295 or is it not 295? It's multiplied 2 by the minimum of these 2 points. Okay, and then those are your p-values. And remember that your sample mean average is a little higher than the what you're looking to disprove, or, sorry, to prove. So that might explain why the p-values are a bit high, but so the alternative is that any questions here? Let's see. So the two-tailed approach is that you can't reject the fact that the null is 295 because the p-value is bigger than the critical value, not low enough. So if you can't reject this, it means that unless you made a type whatever error, then it is true. So if the null is golf balls go 295 and you can't reject that, then that means that that is true. Now, see, this one's a little bit different because so here the null is what you're actually trying to prove. It's 295, and the alternative is it's not. So this one, if you accept the null, that's what you're trying to prove. And because p-values are bigger than 0.05, which is usually the critical value for a p-test if you're looking at like 95% or sorry 5% significance. Because all these numbers are much bigger than 0.05, that's going to tell you that you can't reject the null. If you can't reject the null, that would tell you that in fact these golf balls do go about 295, which is what you're trying to provide evidence for. So let me just, so if you were to just interpret the conclusion. All right, so I'll cover this, but the calculated p-values from this analysis are not less than 0.05, which is the cutoff for 5% significance. So that means that to be 95% sure of your result, your fact that to be 95% sure of rejecting the null, that your p-value have to be less than 0.05. Okay, and none of these are. So the result would be you can't reject the null hypothesis. So that would be the conclusion from this analysis. So the calculated p-values, these ones, from the analysis are not less than 0.05, which is the cutoff for 5% significance. So then the result is that you cannot reject the null hypothesis, and you can conclude that the null is true, which means, or the average golf ball distance traveled is about 295, because you couldn't reject this. So the conclusion is based on how you set up the hypothesis. Um, you calculate the what you compare the p-value to and what you compare the t-value to. And you can see that just to look at the t-stat, that's pretty low too. So normally, like a rule of thumb is that. So I put this here because some texts refer to as the 5% level, and sometimes it's like the opposite, the 95% level. So you can kind of state the significance level as a 5% level, which means your conclusion would be wrong only 5% of the time. Or you can call it a 95% significance level, which means you're 95% sure that the result is true. So either way you state it, like there's a 5% chance of an error, uh, there's a 95% chance that I'm correct. Either way is kind of saying the same thing in a different way. So just know that, like, or just pay attention to the way you're interpreting the significance. Either say it's, you know, there's a 5% chance that you're wrong, or a 95% chance that you're correct. Okay, so the point is that for this level of significance, which is pretty standard, you want a t-value of something that's, the rule of thumb is like bigger than 2. And you can see that in this case it's 1.5, so that would not confirm significance, or that would not allow you to reject the null. And also, you'd also like to have, to reject the null, you want to have a p-value that's less than 0.05. So for the 5% significance level, or the 95%, so either saying that there's a 5% chance of an error, or there's a 95% chance that you're correct, you're normally looking, if you want, you're normally looking to reject the null hypothesis to have a t-value bigger than 2, which is not the case, or a p-value less than 0.05, sorry. Those should be the same kind of result, and so you can see that this is too low, and this is too high to reject the null. Okay, so that's kind of how you would do it if you had just, so basically if you had a bunch of data on something, you can kind of set up these little calculations and go ahead and set up your hypotheses and confirm your result based on the test stats and the p-values, and if they're bigger or less than the critical value, and what that tells you about rejecting the null or not rejecting the null. Okay, so for this one, this worksheet I have here on just the tab where you have where you calculate the sample means and the t-stats, all this stuff here. And then the interpretation of the conclusion. And if you want, you can talk about what your rule of thumb cutoffs are here. But just to have the calculations and then the conclusion is what you're looking for this problem. Is everybody good so far? Any questions? Okay, let's do another example like this using Excel. And the next one is, sorry, the next one is figure 9.8 on page 424. And it's a similar example to this, but a little bit different research question. So if you go to page 424, and let's open up that template in a second. All right, so this one is roughly on page 424 in the textbook, and we're looking at this one, I think. Oops. And we want to open up the data file for orders, ORDERS. Okay, so in this case, well, let me open up the data file. So for orders, all right, so there's a certain number of units ordered, and the goal is to test if the units per order are roughly 40, right? And if they are, or if you can reject if you can reject the null, you can confirm that they are 40. If you cannot, then you need to do some further research and confirm that the average order is not 40, right? So working with the first data file here, let's just cut and paste the let's cut and place the headers with the calculations and then go from there. All right, so if you take the sample size through the p-value 2 tail, on the other tab and put it back on the data tab, okay. So our sample size is just the number of observations or samples, so that's going to count A2 to A26, so that should be 25. And And then the sample mean is just the average of all the units. And we're hoping for an average of something no different than 40, but let's see what just the regular average is. Average of A2 to A26 is 37.4. So that's close, but we got to investigate. Okay, you can calculate the standard deviation of the sample by just standard deviation dot s of the whole all the observations. Okay, standard deviation of A2 to A26, 11.79. This is our null hypothesis. Is the average units per order 40? Okay. And the standard error is calculated for you, but the standard error is the standard deviation divided by the square root of the sample size. We did that by hand on a worksheet a couple weeks ago, but you can use the simple calculation, just standard deviation divided by square root of the sample size. Okay, the test stat for this one, and again, we're manually, Excel's calculating this formula for you. This one here, the equation 9.1, that's what you're doing in this step. All right, so that is the mean minus what you're assuming it's or your hypothesized value is, and then divided by the standard error. That's your t-stat. Degrees of freedom are usually not usually, they're the number of observations minus one. Right, so 25 minus 1 is 24. This calculates the different tails of the p-value based on the t-stat and the degrees of freedom. So what you see here is that obviously if the t-stat was higher, the absolute value, or you had more degrees of freedom, the p-value would go down. All right. So what you can see is that you get the same conclusion, but a different interpretation. Okay, so see, these are like holiday toy orders, and so because the p-value is bigger than the alpha, which is our rule of thumb is 0.05, and then our rule of thumb for the t-stat is 2, we can't reject the null, and that will tell us that if we can't reject the null, which is 40, then we have no evidence to say that the average order is not 40. All right. So I'll just restate the the same thing we're looking for the t-stat and the p-value, and then the conclusion. So for 95% significance or 5% significance, however you want to look at it, All right, so for 5% significance level, the test statistic t should be greater than 2 in absolute value, and the p-value should be less than 0.05. And that's just a rule of thumb. And you can see that the t-stat is not less than 2 in absolute value. All right, and then you can see that all the p-values are greater than 0.05. So that's essentially double evidence, or double evidence, but looking at it two ways, in which if this isn't less than 2, and this isn't bigger, sorry, not not greater than 2. So, okay, so sorry, if this is not greater than 2 in absolute value, and this is not less than 0.05, I wrote them the wrong direction, but right here. Okay, sorry. So if this is not bigger than 2 absolute value, which is not, and if this is not less than 0.05, which is not, both of those tell you that you can't reject the null, right? And if you can't reject the null, that means your conclusion is that 40 is the right number. So all right, so there's the conclusion in this context. The conclusion is we cannot reject the null hypothesis of it's equal to 40 because the t-stat is too low and the p-value is too high. And then the result or the conclusion is that the average units uh, are the null, which they are approximately 40. So we can't reject this. If we can't reject that, then we have no evidence to say that it's not that. So that's how you can look at a. Uh, I guess both of these were detailed tests because you're looking at is it this or is it not this. Um, but you're looking at is my null hypothesis correct or not correct? You can look at it by calculating the sample size, the sample mean, the standard deviation, and then the standard error. the t-stat based on those things, and then the p-values, and then you can make your results based on if the t-stats are approximately bigger than 2 absolute value, which they were not the case in these two examples, and if your p-values are less than 0.05, which they were not the case in these two examples either. Now, okay, so questions on this material? We okay, great. Um, where's so we went through. Well, the goal here was to introduce hypothesis testing, set up the null, set up the alternative, and then calculate t-stats and p-values, type 1 errors, type 2 errors, what those mean in simple context, and later on we'll introduce more than one variable, but the concepts are similar. So I think we went through exercises 2, 3, 6, and 7, and then figure 9.7 and figure 9.8. I don't think we'll get, well, we're not going to do the appendix 9.1 today because I wanted to do some stuff in RStudio, but I don't think everyone even has RStudio installed yet, so we'll get to that later. But you should have enough material to do the rest. And I think we kind of went through all the examples anyways. So if you want, you can turn in when you're done with it assignment 4 by next week. You don't need to do this part yet because we haven't got to it. So part here. So either we'll cover appendix 9.1 next week and add it to another assignment, or I might just kind of do it as an example. But you should have enough to do assignment 4 to cover this part. Okay, and that should be these ones we did, setting up the hypothesis and defining type 1, type 2 errors. Then the two spreadsheets, or you can put them on the same different tabs in the same spreadsheet. So you really have like one Word document or written document, and then one Excel file. Okay, so assignment 4 just can turn in all this stuff. But we didn't get to the RStudio appendix, so don't worry about that, and I'll talk about it next week. Okay. So why don't we wrap it up here? Because I said it would be about 2 hours, and it's been 2 hours without a break, and everyone's been a good sport of joining the WebEx meeting. So we will be back in the same classroom next week, and then the remaining. This is meeting 4, so we still have 4 more meetings. We're just about halfway through the semester, or the term, whatever you want to call it, and we'll spend some more time doing the matrix algebra and in the other textbook next week. But it's a bit hard to do that via Zoom or WebEx. I did want to cover all this stuff from chapter 9, which I think we got a good understanding of. So you can do homework 4, assignment 4, and post it. Actually, let me make a section to post it before I forget. Okay, so that one can go there whenever you're done with that. And yeah. Okay, so I think that's what I wanted to cover for today, and I'll see everyone back in the classroom next week. And once I wrap up the meeting, I'm going. This is we're recording it, and so if you missed something or if any of your classmates couldn't attend, I'm going to upload it to YouTube. So I'll send out an email to the class when that's done. But you can watch or access this video later via YouTube, just in case you want to go over something again or you missed something. So we have that. But I'm not gonna take attendance today because I'll just give everyone full attendance for this week because I did the WebEx meeting. Um, we won't do that. So any before we wrap it up, any questions or anything else for today in reference to today's material or anything else? Right. Okay. Okay. So it's doesn't seem like we have any questions at the moment, but if something comes up, you can email it or bring it up next time in class. So again, I'll see everyone back in our normal classroom next Wednesday at 6. And thank you all for joining the WebEx meeting and being a little flexible and participating this way. But that's it for today, and have a good rest of your week. And I'll see you back in our classroom next Wednesday. So thank you.
You.
Thank you.